Good morning. My name is Scott Engle, and I'm with Mercury Mission Systems. So Mercury Systems, but specifically Mercury Mission Systems, the part of Mercury Systems which focus on flight certifiable computers. And that's what I'm going to be talking today about 2008 being the year that we actually see some significant progress in the certification of multi-core processors. And by certification, I mean FAA or EASA certification for flight safety. Is there anybody in this room who is not using a smartphone? One or two. So I'm impressed. But I also met you last year, so I believe it. So those smartphones are all running multi-core processors. Apple Watches that probably several of you have on there running multi-core processors. But the avionics that we all flew in here in those aircraft are probably running single core processors, but if they're multi-core processors, they're all but one of those cores are disabled. Now it's kind of crazy at this stage of the game that we're still running with single cores on the avionics. In 2008, 10 years ago, I was a young FAE for a software company running VxWorks 653 on 2 cores at the time on an 8641. And 10 years from now, we're still not where certification of a multi-core processor is common. So the things are in place now, though, that I think 2018 you'll see some significant progress. Are you going to see companies come out of certification in 2018? Maybe, maybe not. Certification takes a long time, but there are things in place now that are making it much more achievable. So a brief history of avionics processing. Starts off, of course, with lamp-covered avionics in the front from an old analog. A federated system is one in which most of the avionics or the functionality is special purpose. One computer, one box has one functionality. It does one thing, does it well, does nothing else connected to the rest of the system. The future, though, the future is actually today is we're using a much more integrated technology, and which is called IMA, or Integrated Modular Avionics. And I have a slide that kind of shows about that. Again, the federated system, most of those are connected via some sort of bus, ARINC 429, for example, for civilian, or 1553 for a lot of the military systems. But they were all discrete functionality boxes. Now we move into a more integrated IMA's Integrated Modular Avionics system, where on a single core system today, future will be multi-core system, you're putting a lot of functionality all on the same box. Today, it's all on the same single CPU, and on that CPU there has to run an operating system or a hypervisor that does temporal and spatial partitioning. So, are there any single people here? None. Well, good. If you go to a party and you talk about spatial and temporal and spatial partitioned operating system, you'll stay single. So I'm just going to warn you that that's interesting topic, but not very exciting. Again, federated system, very distributed, very single function. IMA, where everything is completely integrated. The problem with a IMA type of system, you generally have to build it from the ground up to be integrated that way. And that poses a problem for a lot of our, especially for our defense customers. The future of avionics is going to be much more information-driven or knowledge-driven, possibly deploying things like artificial intelligence and deep learning neural networks. We're already having customers asking about doing that. The problem with that is now you're taking technology that has never had a safety pedigree, and you're trying to incorporate it into avionics, which will be very difficult initially. There's a trend going on that's actually kind of interesting, is you are seeing some of this technology enter into a safety situation outside of avionics, outside of aerospace, such as the auto industry. So you'll see a lot of this technology first introduced into a non-flight situation, which is kind of great. You don't want the your flight or your computer in your aircraft learning as it crashes, so that the next aircraft doesn't crash. You don't want to be part of that. So let's let the other markets handle that, or industries handle that, and then we'll learn from it and deploy it in aerospace and defense. Many of the systems that we see are really stuck in between the federated system and the IMA. That's really true with defense customers because they don't have the opportunity to completely redesign. They're continually, what we say, integrated without adult supervision, and that's not entirely true. It's just that as new functionality or new threats or new requirements come on board, typically those are integrated individually and not taking the opportunity to integrate the entire system or redesign the entire system. It would be just too cost prohibitive. The other factor is that there is a overwhelming desire because of the high cost of certification to reuse as much of the previous components as possible, and that's generally a barrier to integrating and doing things in a much more integrated way. So what does this mean to multicore? Well, we're no longer able to get dramatic improvements in CPU performance just by increasing the clock speed. Where we used to get 30% performance per year or per Moore's law cycle, we're only getting 10%, maybe even less a few times. But that trend's not going to continue just living off of clock speed. Big thing, though, is that processor companies are frankly not that interested in producing our single-core processor. We are going to have to live with multi-core processors in the future. And somebody was just talking about GPUs with thousands of cores in there. Well, I don't want to fly a plane with thousands of cores in the CPU, at least not in the near future, but that type of situation is coming where that's all that's available. With this multi-core, you get some very interesting, but also somewhat unknown capabilities of mixing criticality. And by criticality, I mean in safety there are generally five different levels of criticality that will define how the system has to be tested. So for DO-178, for example, there's a level A all the way through level E. Level E might be the laboratory occupied signs. Really don't matter if those stop working. Inconvenient, yes, but the plane's not going to crash. The flight controls, autopilot, things like that are level A. If those things stop working, the plane doesn't work anymore. So that's why mixed criticality in those multi-core systems presents a lot of different options, a lot of very configurable options. Do I use homogeneous cores? Do I use heterogeneous cores? Do I use the same operating system on each one of those cores? How do I partition that system? There's an awful lot of choices, and the experience we'll have in the next couple of years will dictate what are the best choices going forward. The other thing that's obviously very important, especially when you talk about unmanned systems, is the ever-increasing design or desire to lower the swap or the space, weight, and power on that system. So what are some of the historical factors that we use to just determine what CPU we're going to use? Performance and power dissipation were the main things. Whether or not that CPU is going to go obsolete in the next few years, obviously. The technical readiness level, or how long it's been in service, and whether or not it had a certification history in the past. One of the things that's common with certification is you do not want to be the first one to go through a process with anything new, which has also been one of the factors why certification of multi-core has been delayed. Nobody wants to be the first. The other thing is, are the detailed informations on the design at a low level available for that CPU? In the future, we're still going to have many of those same factors, but determinism and isolation will be an increasingly big factor. And that determinism and isolation is all around whether or not you can maintain determinism with multiple different cores and applications running on those different cores. What's also a big factor is the software ecosystem. That the RTOS companies who provide certifiable operating systems, which cores that they're going to be supporting, the flexibility of those cores, again, talking about whether they're homogeneous or heterogeneous or what type of architectures they are. And there's still a lot of uncertainty about the future of what will be the safety silicon of the future. With PowerPC bowing out of the safety market, will it be ARM, will it be Intel, what will it be in the future? So there's still a great deal of subjectivity around that. What are unique to avionics? The avionics systems have to be in place for 20, 30 years, a long time. There's clearly a certification requirements, talking about the determination and isolation already, but the cost of certification and recertification are enormous. And And the last thing is there's also a security need. So when you have multiple applications running on the same CPU, you introduce some ability to share inadvertently data and lose some control over that flow of the data. So while safety and security are generally not thought of together, we are going to have to address them in the same system in the future, much more so than we're doing today. The root of the problem, it's not the T2080, but the T2080 slide I'm showing here just as an example, is that there are always some shared resources. And this shared resources because the processor companies are not designing processors specifically for safety. You can notice that on the T2080, up here at the top, you'll see if those cores are actually using both threads, they're going to be sharing data and instruction cache. There's clearly going to be some L2 cache that's shared between those cores, as well as the processor control bus. But PowerPC architecture isn't alone. You can see with an Intel Atom, there's shared L2 cache. Every processor that's out there that's of any significance in the market will have some shared resources out there. And that's the root of the problem. There's always some level of shared resources, whether it's memory controllers, whether it's cache, whether it's a bus. And it's just the fact of that we're using processors that are designed for the enterprise or the commercial market, for our cell phones, for our desktops and things like that. So the use of shared resources always creates interference. Always, most of the time, creates interference, some type of interference. And by interference, I'm talking about if an application is running on core 0 and you have a different application running on core 1, core 0, that application on core 0 can impact the performance of that application running on core 1, whether it be through the inability to gain access to resources that it needs, or is just hogging up more of the bus or things like that. The amount of resources or contention or interference that is possible increases with the number of cores used. So using 2 cores might be bound, might be reasonable, might be understandable, but when you get to 4, 8, 16 cores, that's really going to be difficult to understand, especially going in. And every use case, every application is going to be different. So it's really hard for a system level person to look at a design and say, I can understand at the beginning of that application design what the impacts of the different interference is going to be. So it's very use case limited. That may be a big factor in what operational choices or architectural choices are actually used in certification, what the certification authorities, FAA or EASA, may actually approve. But all that bad news, there is some good news. The certification authorities are coming around to much better understanding of the multi-core problems or multi-core situation. They're introducing a lot more guidance. The CAS32 papers was first introduced a few years ago, and they've actually have an update to it, CAS32A, that addresses certification of multi-core. There's an evolving standard of Avionics 653 that's becoming more multi-core aware, and there's working groups that are created specifically to address multi-core avionics. Interference is becoming better and better understood. The operating system companies are doing a very good job of testing the different cores, and they have to test each core independently through a myriad of tests. The tests are actually consuming much more of their time now to help understand what are the impacts of the interference. And then the hardware companies, Mercury, for example, are working closer and closer with those software companies to actually understand and then communicate those interference issues to their customers. So there will be simple multi-core designs that are going through early. We'll learn a lot from those first couple rather simple multi-core certification efforts, and that'll apply that to allow us to do much more complex things in the future. So one of the things with IMA, one of the new capabilities is there is a standard called DO297, or role-based separation, where it defines different roles in the creation of integrated modular avionics. And those are platform suppliers, which are generally the hardware companies. The system integrators, they could be a aircraft manufacturer like Boeing, or it could be the designer of some complex Avionics, and then there's actually an application supplier. So an application supplier could be just about any company who writes software to design things like an autopilot or some navigation code like that. So an application supplier would be contracted by a system integrator to provide applications that are going to go on that aircraft. IMA is pushing everybody to think much more systems-wide, which before they were in a federated system, they were allowed not to think in the systems terms. So IMA is really pushing people and everybody on the whole software or the whole chain to think more in terms of systems. There's also a greater number of requirements and constraints that are being put on the application developers, and those are basically around their understanding of the interference and the multi-core problem. There's a tighter partnership that's going on between the hardware and software companies, and then there's also, because of those huge number of architectural choices, there's those choices or the desires and requirements of the applications will actually a lot of times dictate which of the CPUs that are being chosen in this environment. So in summary, our understanding of multi-core is getting a lot better, but also I think the industry's comfort level around multi-core is getting a lot better. There are already, again, some early certification efforts in process through various stages. Some of them are more complex than others, but we're learning an awful lot as an industry. Vast number of architectural choices, both hardware and software choices. Collaboration is a must. Collaboration early on is even better. And the platform provider and the customer need to work together much more closely to ease that certification effort.